Hi again, and welcome to today is Tuesday, March 11th. I just want to bring your attention to a couple of things. First of all, I'm having issues recording these classes from this point on. It seems like Zoom is not processing the recording in time, okay? Actually, I have a class from yesterday. It's more than 24 hours now, and it still says processing recording. For some reason, it's not available, okay? So I'm going to try to send a message to everybody else to understand that this is an issue. So your guys are strongly urged to attend the class live because of this one. Furthermore, it's probably a good idea to subscribe to the YouTube channel still, because once these things are available, you will receive the notification directly from Google that there is something is up. For your class, you really pay attention to two things in here when you're looking for stuff that is related to your class. The first letters actually of your class should say PHY4B. Okay, not only that, for your class, you're going to watch for the next three numbers, 333. Okay, that is actually your class in here because there are so many classes, and that's the only way for me to put them when I'm putting them on YouTube. Obviously, later on, once they're posted on YouTube and indexed by YouTube and put back on YouTube, I go back to Canvas and give you the link so that you guys can see it. So if you want to wait that long, that's fine. So that is one thing. So please pay attention to that. Again, if Canvas does not give me the recordings now, so I probably have to resort to a different way of recording these classes. But I'm not hoping not to do that because that's going to really chew on the computing power. This computer is supposed to have 32 gigabytes of RAM, but I don't know. We'll see. Anyway, that's one thing. The other thing also is there is a time change, I think, this weekend. I'm not 100% sure, but I heard it somehow in the news in the morning when I was making my coffee that, so I'm not paying attention to exactly what's going on, where we are in time, so on and so forth. Always have to look at the computer to see where we are. So again, that's basically a couple of things that you have to do. So I'm going to basically monitor the situation with Zoom, and if it develops into something that is really a problem, I'm going to send you guys a message and let you know what's going on. Okay, so this is in terms of that. Today, we were supposed to get into a new chapter, actually. I'm not a new chapter, I'm sorry. We were supposed to do problems from this chapter. Let me find the book, okay? If I can ever, I don't know where I put it. Hold on a few guys, okay? So we're supposed to do the 15th edition. There was a question from one of you guys the other day about the problems and how to find them if you have an e-text. And actually one of you guys was able to answer it quickly and says that, hey, if you go to the e-text, every chapter has at the end of it the problems and discussion points. Let's go there and basically do a search and you will find the problems. So chapter 23, I promised we're going to touch on problems 41. We're going to do problem 41. We're going to also do problem 61. We're going to do, we did already problem 76. Didn't we? Yeah, we did it. Okay, we did the entire problem 76, which was kind of fun problem where we went actually in detail about, they gave us a potential in problem for 76, V as a function of, okay, you guys, I'm not sharing the screen, am I? Sorry, should have spoken. So basically, where problem 76, they gave us a potential as some function of x, y, and z. And from here, we were, and they had this potential was defined within a constant. So given the information of the work that was given to us for a charge to be moved from one point in space to the next, basically, we used this formula, V of, I think we ended up at 0.000 in that problem, minus V and the initial points, which I don't remember exactly, but I think it was 0.01. I'm not sure, okay? You guys need to check on these numbers, or probably 100 or something like that, and ended up in there. And that was Q. They gave us it's 1.5 microcoulomb. And we have V in function of X and Y and Z. All we had to do is plug V there. And we have V in function of X, Y, and Z. All we have to do is plug in there. And we know what this number was. It's, I mean, it depends on a parameter A actually. So the difference we can find, actually this number turned out to be 0. And this work actually is given to be somehow equal to 6 micro or 60, some value in there. I don't remember the details, 60 microjoules or something like that. Anyway, we found A. So we used the work to find A. Once we have A, then we were in business, basically. We should have been actually able to find the electric field. The electric field basically in the X direction and the Y direction and the Z direction is just minus dV over dx until you get into a minus dV over dy, dz, I'm sorry. There is a minus dV over dy if you really like that. So at the end, we have the electric field, we calculated it somewhere, and then we have everything for this problem, basically. Okay, so that was problem 76, okay? And then we have another problem that I promised actually we will do, and that's problem 77. So out of this 4, we did problem 76 last time around. I'm hoping that you guys have had a chance to go through that derivation and make sure you understand every single step. And if you have any questions, again, you let me know. And if I made a mistake, please correct it and let me know so that we can, so that everybody benefits from it, okay? So this is basically the problems that we just said we will do in this chapter. I know I talked that problems 46 is actually a fun problem where you're just plugging the numbers in there in 46. So you have a bunch of charges in there situated some distance, so you're supposed to find the energy in there, okay? Problem 57 is identical, except that that's a practical problem because that's a problem that deals with the sodium chloride. So you have charges and you're supposed to find the potential and things like that, and except the charges are given in units of Q, so they're not given in, you don't have numerical values for problem 57. I mentioned problem 62, actually, which is the Geiger counter Mueller, which is really not too different, honestly, than problem 61, which is the coaxial cable, the problem that we're going to be doing today, okay? And then I mentioned also problem 77. Problem 77 is a data problem, and you know how much I like those problems and how to solve them. Basically, because that's what physicists deal with, trying to model things that they actually go to the lab and measure and then try to find answers to the questions that they have in mind and answer them. And that is really a practical problem. Okay, so those are the problems we promised to do. And we're going to do them. And I'm hoping that you guys, look, physics, as I mentioned before, time and time again, is all about doing, not about basically watching other people do. So you have to do these things. Either you do them live right now, so I'm assuming that some of you actually have a piece of paper right now and a pen or a pencil and following with every single thing I'm writing in here and making sure it makes sense to them and slowing me down and actually taking the time to go through the analysis and the discussion so that it's perfectly clear for you. If you're watching this one also recorded, you're doing the same thing. You have a piece of paper handy and a pen, and you're starting this one. Now, I know at least a couple of you right now who don't have that piece of paper, so I'm going to give you about 30 seconds to grab one and a pen. Yes? Time is ticking.
Professor, I have a question regarding the discussion board. I already have a pen and paper out.
I'm waiting for the 20 seconds to expire so that
Yes,
everybody
so
has.
while they're doing that, I wanted to ask you, for the discussion boards, are we posting like a summary about the lecture, or are we posting the answer to the questions that we got?
The questions that you're asked for this problem sessions is actually going through the numbers, okay? And making sure that the numbers make sense, then everything is calculated and finished and all of that, okay? So what you're saying in there, yes, problem 41, this is the answer to it. Problem 61, this is the answer to it. Problem 77, this is the answer to it. Basically, to tell me that you're actually doing the work and actually honestly doing the work and not just copying what we're doing here and trusting that you guys are done and have your piece of paper. Now, here is what I really don't want, okay? Here is actually the bad thing, which is going to really be detrimental, especially since we are online. If we are in class, there's a different approach that I do, okay? that somebody will sit in there watching the whole session being developed for an hour and a half and being distracted probably by a message that he or she receives by the phone, and then just listening. That's not going to stick at all. That's not going to be very helpful at all. So I really want you guys to pull your sleeves and do these things. That's all I want from the discussion, honestly, Priscilla, and everybody else. Okay?
Okay, so you want to see our understanding. Like, so if we have a question regarding the question, like we'll write what we had a question on and how, like, we got, like, what we didn't understand in our answers.
Yeah, that's fine. If
Okay.
the reason, for example, let's say, for example, in going from this step to that step, it's still fuzzy for you. I mean, you looked at it again and again and again and again, and you probably wrote it time and time again, but it's still bugging you because why in the world do we have to do that? That is actually a great question. That is something that it needs to be clarified. We don't want anybody to be thinking that there is some mystery in here or some magic in here that is at work. We want to have everything clear. So that's actually a good point in there to raise the issue. Yes, I see what you did, but why though? You understand what I'm saying in here? That's actually a great question that enrich the topic and makes sense to you. Once you're comfortable with it, once you know that that step is necessary, then you're good. That's why when I solve these problems, I tend to be too verbose. One problem will take probably half an hour sometimes for me to do. If I'm doing it on a piece of paper, probably I'm working on it, probably it's not going to take that much time. Okay. And that's what I expect from you at the end of the day, not to take that much time, because we want to hammer it from this angle, from this angle, from that angle, from the other side, and see what it leads to, what it could do, and all of that. So we're having actually a discussion while we're doing these problems. It may be boring at times for you to make that discussion for what looks obvious to you, but bear with us, basically, so that actually we can develop these ideas and move on with them. Okay?
Okay, Professor, thank you for the clarification. It's because I know that we have a discussion board, two of them due on the 12th, and I wasn't sure if you just wanted us to put the answer or if you wanted us to elaborate on it. Because I thought, like, if everybody's just posting the answer, like, but that makes sense. We can put like our little notes as to why you got this or why we took that step.
Yeah. Okay. Honestly, Marcella, you have the freedom to basically put either. Okay. So as
Okay.
long as you're posting your answers in there. So if it's, for example, a quick answer, the E was there, the B was there, whatever the value that we have in there, that's fine. Or if you want to elaborate on it, that's fine too. And I honestly like the one when you elaborate, that shows confidence, that shows actually knowledge. But the point being in here is that the secret in the whole thing, the purpose of the participation in the whole thing is that you guys do things. You don't watch me do things, because if you watch me do things, well, I know this stuff. I have done it many, many times, and probably I made a mistake many, many times, and it's washed away. So, but you guys are not going to retain these things, okay?
Yeah.
When it comes to a real problem that you have down the road, or in an exam, or it's not going to look like this one, but somehow you have been trained enough now to look at that problem with a new eye and hopefully process it and work with it. Okay, so that's what I'm hoping to achieve. So I assume by now every one of you guys has a piece of paper and a pen ready to write these things. Okay, unfortunately
Yes.
for you, unfortunately for you guys, we're going to finish the lecture first, because there was an item that we didn't finish from chapter 23, so that we close the book on it, and then we're going to move on with these problems. Okay, can we do that?
Yes.
Thank you. So we have a negative charge, a positive charge. We called this one an electrical dipole, if you guys remember. And when we did it in class together, we calculated the electric field in here, and we found it to be pointing in this direction. Okay, the distance between the two charges was 2a. In other words, the distance, if I go right smack in the middle, is a on each charge. Okay, so this distance from the negative charge to the positive charge is 2a, not a, 2a, the distance between the two charges. We define the dipole in this case as just being the charge, which is either, because the two charges are the same magnitude except they have different signs, times that distance, which is 2a. So this is the distance between the two charges as they stand. As a matter of fact, this P, which is we call the dipole moment, is a vector. So the dipole moment is actually equal to Q times 2A in the I hat direction. This is the I hat direction, okay? In general, if I take this dipole and flip it around one way or the other, it's still pointing from the negative charge to the positive charge. So the dipole moment has this strength, points, which is a vector, from always the negative charge to the positive charge, okay? So that is a vector whose magnitude is the charge times this distance. So 2A, I want to emphasize the fact that it is not twice the distance, it's just the full distance, okay? It's for symmetry purposes that we wrote that distance as 2A, no more. So for example, tomorrow you have an exam where you have a question like this, and sometimes it happens, okay? You have a charge, negative charge that is situated at, it has coordinates, for example, -1, 1, and it has a value Q, forget about the value for right now. And you have a positive charge that is sitting at positive position 1, 4, for example, okay? So this is positive Q and that is negative Q. What I mean by distance is this one. So 2A in actuality, let's say, for example, these are in centimeters, okay? Everything is in centimeter, in a coordinate system somewhere in here. So this is the y-axis and this is the x-axis, okay? So this is the dipole now. So this is negative Q and this is positive. Obviously, I'm not looking at it in this picture. I'm looking at a different picture. So the 2A now is the square root of 4 minus 1, or let's start with the x-axis. 1 minus minus 1. So it's going to be plus 1 squared plus 4 minus 1, the whole thing squared under the square root. So it's going to be square root of 4 plus 9, which is square root of 13. Okay, square root of 13 in centimeters. So that is 2A. So they gave you Q is equal to 5 microcoulombs, multiply that, convert to centimeter to meters, and now you have the magnitude of the dipole. Okay. So if they tell you now this, you can find the direction now of this vector P. It's the vector that points, that has this X components basically, which is actually 1 minus 1. So this is its X component, this is its Y component, and this is actually the actual vector itself. So you can draw the vector by taking that divided by the square root of 13. And now you go back into chapter 1 or 4, or I don't remember exactly when you had the vectors introduced from physics 4A. So again, the only reason why we wrote it times I hat in this situation was because of the fact that the direction from negative charge to the positive charge was by choice, actually, to make life easy for us along the x-axis. We calculated the electric field in here. And far away, we found drops like 1 over the x cubed, okay? We found the electric field in here too. And it has to do with P also in the numerator. Okay, I didn't try the 2 pi epsilon naught in the denominator, but I'm assuming that what I care about is P and x cubed now, that's all. Same thing in here. At a distance y, we found it too to be some P over y cubed, also far away. We call this far away business, meaning when y is super big compared to A, or x is super big compared to A, the dipole approximation. So we found those things, okay? Now, those are two restrictive locations. How about anywhere in space? That's basically where the power of the potential now comes into play. So we're going to find now the electric field everywhere. The reason why the dipole is critical, because it has analogies with the magnetic field, which is coming down the road, and also because actually it has an importance of its own. This is how antennas work, actually. They're dipoles, okay? So we found that we want the E field everywhere, not just in those 2 points, okay? So here's a positive charge still. There is a negative charge still. The distance between them is still 2A. So this is an A and this is an A. I'm going to take this one as the origin of the axis, 0, 0 in here, okay? So that is the origin of the axis. I want to come to this point in space, P, that has coordinates X in the X direction, and that has coordinate Y in the Y direction. And I want to find the electric field here. If I were to use chapter 21, first of all, I can't use chapter 22 at all. I cannot use Gauss's law because there is no symmetry in here. It's very hard to do, okay? The direction is going to be a mess and you'll have cosines and sines everywhere, okay? But if I were to use chapter 21, what I do in this case, I find this vector. This is a positive charge, so the electric field will be pointing this way. This is a negative charge in here. By the way, this is the vector r of the point P, okay? The one that has the x coordinates. So r, by the way, is equal to xi hat plus yj hat. Because I know it's x components and it's y components. In this coordinate system where the origin is the center. Now, I need this electric field. So there is a repulsive electric field. There is a Pauling electric field. So this one, albeit this one is weaker than that one because the charge clearly in here in this case is closer to the positive than the negative. The electric field is somehow going to point this way, the sum of these two vectors, okay? And then I have to deal with the cosine and sine, and it's going to be a nightmare trying to do that with chapter 21. Instead of doing it with chapter 21, we're going to use chapter 22. Find the potential in here, V. Once I find V, I take the derivative of V with respect to x and z, and we're done. We found the electric field. Okay, so that is really the whole purpose of it. So for that V, I'm going to assume it's actually the sum of the two V's, the one coming from the positive charge and the one coming from the negative charge. For that, I need this distance, the r plus, and I need this distance to the r minus. Make sense? Because these two are point charges, I know that the electric field due to the positive charge is 1 over 4 pi epsilon naught times q over r plus. And the one coming from the negative charge, because it's a point charge, it's 1 over 4 pi epsilon naught times the charge, which is negative q, by the way, divided by r minus. Add these two numbers, one of them positive, the other one is negative, and I have found V. Now all I have to do is take its derivative. The only nagging thing in here is that r plus and r minus, I need to express them in terms of x and y. That's all.
Isn't
yes.
r plus on the bottom squared?
No, for the potential, no.
Oh, okay.
For the potential of the point charge, the whole point of it is that the potential of a point charge is 1 over distance. That's it. Remember, we integrated 1 over r squared, and when you integrate 1 over r squared, it becomes 1 over r. Because the electric field is the derivative of this guy. So the electric field has 1 over r squared. So the electric field, which is a minus gradient of the potential, if I take the derivative in the radial direction, of course, it will be only minus the d with respect to r of this something something over r. I'm ignoring the something something. So now this will become 1 over r squared. Make sense?
Yes, thank you.
Okay, no problem. So the potential has no r squared in it, just r, the distance, period, end of the story. So if I can find that r plus and r minus, we're in business. Okay, so let's do that. I'm going to look at r plus, which is actually this vector, as a vector. And look at this vector. This vector is clearly, this is I hat, by the way. This vector has a length a, so this vector is a I hat. So I have a I hat plus r plus. Isn't this r itself? You guys agree?
Yes.
Yeah, so it looks from the geometry like r is simply equal to a I hat plus r plus vector. So from this, I can pull what r plus is. R plus actually is equal to r minus this a I hat. But I know what r is. I know its components. It's xi plus yj. So actually this vector now is xi hat plus yj hat minus ai hat. All I have to do is group these things together, and we're in business. So it's x minus a I hat plus yj hat. And all we care about is the distance. We don't care about the vector itself. So r plus from previous classes and vectors is just the square root of the x component squared of this vector, which is x minus a squared plus y squared. So that is basically what r plus is. So all I have to do is plug that in that expression, and we're done with v plus. I need to do the same thing for for r minus, though. So let me look at this r minus business in here. This is a vector that is the sum of this vector which has the length A and pointing in the I hat direction. This too is A I hat. It has the length A and pointing in the positive direction of the x-axis in the I hat direction. And this is R. So if I add A I hat plus R, isn't that R minus?
Yes.
Yeah. So R minus now is simply equal to A I hat plus R. Again, R, I know what it is. So this becomes A I hat plus X I hat plus Y J hat. And now I group these two terms together because both of them have I hat in it. So it's going to be X plus A in the I hat direction plus Y J hat direction, J hat. Now I can find again the magnitude of this vector R minus by simply taking the Pythagorean theorem in this case using its components, X plus A squared plus Y squared. Now I have found what R minus is. And I have R plus is. Don't forget R minus has a minus charge in it, coming from negative Q, okay? So the potential now is going to be, just the sum of these two potentials. So V is going to be equal to Q over 4 pi epsilon naught, it's the same number. Open parentheses, 1 over R minus, which is the square root of X minus A squared plus Y squared, minus 1 over the square root. The minus has to do with the charge, okay? It's because I have a minus Q in here, okay? The distance to the negative charge has a plus in it, actually, in the denominator. X plus A squared plus Y squared. And now I have found V as a function of X and Y. Of course, A is there, and that is because of the property of the dipole. A is the half the distance between the negative charge and the positive charge. That's all. So that's why I wrote 2A. If we didn't write 2A, we would be dealing with the distance over 2, and we'll have a factor of half every which way. And that's really the annoying part of it. So by symmetry, we just use that distance as 2A. But this number in here, if I go back to my practical example that I started with, is just square root over 13 over 2. So A is square root over 13 over 2 centimeter, of course, okay? So you have to make it into meters to have the units match in volts. So that's basically in a nutshell what the electric field is. I mean, potential is. So theoretically, from here, you can find it everywhere. Because if you want to find the electric field in the x direction, all you have to do is take this guy and take its derivative. And if you want to find the electric field in the y direction, all you have to do is take this derivative, and you are in business, okay? So this is just like any other function, any ordinary function, so technically you can find it, okay? Make sense?
Yeah.
Okay, usually though, we don't really use this problem this way. We use the dipole approximation. And for that, if I take the distance R super large compared to A, what I mean by R is the point P is far removed from, it's very far, okay? Very far from the charge. That means its X and Y are super big compared to A, okay? So I can ignore A squared. So we're going to ignore anything A squared or higher. Just keep A. Because if we don't ignore A, we're going to get 0. If we ignore A, we're going to get 0. So we don't want to ignore A. So we need to keep at least one order in there. Okay? Because far away from the two charges, they are actually neutral. That's why you have 0. But we don't want to be that far. We want to be just far enough to cancel anything A squared or higher, but keep A. You guys understand? So this denominator has an x squared plus an a squared, which is 0, which is going to be dropped right away, minus 2 times a times x. That we will keep. Okay. This denominator has an x squared plus an a squared, which we're going to ignore, plus 2a times x. So this is the dipole approximation, by the way. What we're doing now, we're doing the dipole approximation. So this this voltage, I'm sorry, is going to look like this. The voltage is going to be equal to Q over 4 pi epsilon naught times the square root of, I have a big parenthesis in here, of x squared plus y squared minus 2ax. I just rearranged this expression, that's all. Okay, where a squared is being ignored. So I just took the last term that has a by itself, okay? Minus 1 over the same thing in here, square root of, again, y squared plus x squared. Why did I change this order? I don't know. 2ax. Okay, so understanding that a squared is not 0, but it's practically 0. It's negligible compared to everybody else. Have you guys remember Taylor series or not from your math class? Did you guys do that?
Yeah, we did that.
Okay, so that's basically where we're headed with this thing, okay? So what I'm going to do is I'm going to pull y squared plus x squared and y squared plus x squared from the square root, from both of them. And note the following, that r itself is just the square root of its components. So actually, when I pull it, I'm pulling 1 over r. So v then is equal to q over 4 pi, where r is actually the distance to where that point is we're interested in. So what I have in here is 1 over r, which is this number, by the way, times 1 over the square root of, I'm left with 1 in here when I pull x squared plus y squared. I pull them both, minus 2ax divided by x squared plus y squared, which is just r squared, minus the same thing. I'm pulling x squared plus y squared, which is under the square root, which is just r by itself. When you pull them with the square root itself, it's actually r. And I'm left with the square root of 1 plus, again, 2ax divided by x squared plus y squared, which is r squared. So I'm going to leave r squared in here. So far, so good. This is pure algebra. This is not really any more approximations. But note the following. 2ax over r squared is small. Although x and r are of the same order, but a over r is tiny. A over r is a lot less than 1. And a over r in here is a lot less than 1. So I'm going to use this approximation that basically from your Taylor class that says the following. The square root of 1 plus a tiny number, I'm going to call it epsilon, or minus that tiny number. So the plus would work here, and the minus would work in here. So is equal to roughly, ignoring anything of the order of epsilon square, where epsilon square is actually a squared over r. So it's going to be roughly equal to 1. If it was a plus, you put a minus. If it was a minus, you put a plus. 1/2. And the half is coming from the derivation. When you take the first term in the derivative for the Taylor series from of the square root, you're going to put 1/2 of epsilon, plus terms that I'm going to ignore of the order of epsilon squared. So I'm going to ignore those higher order terms. Okay, so the plus will give me a minus, the minus will give me a plus, and my epsilon in this approximation is simply 2ax over r squared. It's tiny compared to 1. Okay, so I'm going to write this expression using the Taylor in this far away region from the dipole, 4 pi epsilon naught times. Okay, I have a 1 over r that is common to both of them, so I'm going to pull that r out. And I'm left with 1 over the square root of 1 minus epsilon. 1 minus epsilon is 1 over plus epsilon. So it's 1 plus, and epsilon is 2ax over r squared. Minus, okay, open parentheses. Again, 1 over 1 plus the square root. The plus square root will have a minus in it from the Taylor series. 1 minus, oh, I'm sorry, I forgot the 2 in here. There is a 2, epsilon over 2. Okay, there is a 2 from the Taylor series that I need to pick. The same thing in here, it's epsilon over 2, and epsilon is 2ax over 2r squared. Okay, obviously the 1 and the 1 cancel, and the minus becomes 2. Obviously the 2 and the 2 and the 2 and the 2 cancel, but I'm left with an ax over r squared plus ax over r squared, which is 2ax over r squared. So this whole expression then becomes closer to Q over 4 pi epsilon squared times 2ax over r squared. And don't forget I have an r already in there. So this expression becomes equal to Q times 2a, which is my p, by the way, divided by 4 pi epsilon naught times r cubed. This is p, this is x. So this potential then becomes p times x over 4 pi epsilon naught times r cubed. Exactly the expression that we had before with an r cubed. Now this is not the electric field, this is just the potential. And it's a number, this is a scalar. Okay, depends on x, depends on y too through r cubed in here. So we could potentially take the derivative of this guy with respect to x and y. The same thing, far away, of course, from the dipole, but not too far. Basically, if you take the water molecule, at least some distances away from the size of the molecule. Few basically what? Maybe 10 nanometers or something. This would be perfect, okay, for the water molecule. It works perfectly there, okay? This is exactly the model for it. Now, x, if you remember, is the x component of the vector r. P itself is in the x direction in this case. So x times p is nothing but p times r as a vector, because the dot product of these two vectors is just this expression. So this expression can be written as p times r, because that is actually what px is. Because this p has no x component, so that's exactly what that number is, divided by 4 pi epsilon naught times r cubed. The reason why I can do this now is because I can use polar coordinates. Remember, the vector r in polar coordinates has direction, has an angle, has a measure r in length, but a direction theta. And direction theta is actually with the vector p itself. So I could use this product actually using the properties of the dot product and say that this is actually p times r times cosine of theta divided by 4 pi epsilon naught times r cubed times r cubed. You cancel the r cubed in here and there because it was a false indication here that depends 1 over distance cubed. It does not. It depends on 1 over distance squared because I have a distance also in the numerator. And that's clear now in polar coordinates. It does not, because now the potential is actually depends on it's p cosine theta over 4 pi epsilon naught times r squared. Now, if I take the derivative of this guy, I will find the electric field that depends. Because when you take the derivative of 1 over r squared, you're going to get 1 over r cubed. So this is perfect now. Okay. So again, this result actually used to be part of a homework in another textbook that we used to use, not in. I've got the title of it right now too. It's not Holiday Rhythmic. Holiday Rhythmic also uses the same thing. It used to be part of a big homework problem that where we can deal with a dipole. Anyway, just to argue the following. First of all, this is the potential everywhere. Once you find the potential everywhere, technically at this point, you're in business. I'm sorry, this is the potential everywhere. That is actually an approximation. That is for r greater than a. We ignored a squared in that one. So this is everywhere in space. And now you can find the electric field both in the x direction and y direction. If you choose to, you could use polar coordinates actually at this point too, and pull the a and the a and the r and all of that. But it's kind of hard and cumbersome. So it's much easier actually to do the Taylor approximation for the dipole approximation and come up with this very nice result that actually will replicate those very same results that we have them. All you have to do is find E sub r, which is just minus dv with respect to r. And for that, it's clearly equal to negative times, it's going to put a 2 that cancels this 2. So it's going to be actually a positive because the negative and negative becomes positive, p cosine theta over 2 pi epsilon naught times r cubed. This is the radial component of the electric field. If you were curious trying to find E sub theta in the angular direction, it's negative 1 over r, the derivative of v with respect to theta. This is in polar coordinates basically on the plane. So again, the derivative of the cosine is a negative sign times a negative, it becomes a positive. So it's going to be a p sine theta over, again, you have an r and you have an r squared in here. So it's going to be an r cubed in here, 4 pi epsilon naught times r cubed. Those are both results in here. That is true everywhere. Okay. The main thing in here, the moral of the story is you can find V, you're in business. And this is the case of the dipole. We're going to come back to this dipole later on, okay, when we come to magnetism. And we actually are not done completely with it in this case too. So we still need a few things from it. We still need the moment and some other stuff in that is needed, and the energy and everything else. Okay. So, problem 41. Any questions about this dipole business? No? Problem 41. Let me read for you problem 41. Problem 41, we're going to do half of it, and you guys are going to finish the other half, okay?
Sounds good.
Okay. So problem 41, it says that you have a metal sphere with radius RA is supported on an insulating stand at the center of a hollow metal spherical shell with radius RB. So basically, you have a sphere. It could be shallow. It could be hollow. It could be solid. It doesn't matter. It's conducting. So if I put charge on this sphere, it's going to be on its surface, end of the story, period. But the other sphere now that is outside, that is hollow. Otherwise, we can put this thing in it. Okay. Of course, you're telling me how we're going to put a sphere inside a sphere. Make a small opening in here and basically put a stand for this one. And that is basically what you're looking at. Okay. So this is a sphere. The inner sphere radius is RA. And the outer radius is RB. Okay. Both of them are conducting. Both of them are conducting materials. And this one has a Q charge. This one has a negative Q charge, okay, on it. So this looks like the capacitor we did earlier. Actually, this is a capacitor too, okay? So we want to find basically the potential, basically find V everywhere. V for R less than RA, for R more than RA but less than RB, and for R more than RB. So that is a question that we want to find. Okay. There is no charge inside RA. Q is equal to 0 because this is for R less than RA, by the way. It's a conductor. They tell you it's a conducting sphere, okay? So all the charge Q must exist on its surface inside this one. That's what R less than RA mean. So there is no charge inside, there is no electric field inside. Because again, if we use Gauss's law in there, we find that E equal to 0. And if we find E equal to 0, that means that E, which is the minus the derivative of V with respect to R, I'm using the radial symmetry in this case. That's why the curly becomes just this straight derivative. There is no dependence on theta or phi or anything like that. You have symmetry, so it depends only on R. So in this case, this is 0. So how much is V is inside? Which function, if I take its derivative, I get 0? Which function, if I take its derivative with respect to R, I get 0? Oh, everywhere. This is the calc stuff.
Is it a constant?
Absolutely.
I was just about to say that too.
I didn't want to be wrong.
You don't have to. No, come on, guys. Just sometimes my questions are tricky, and you're thinking maybe he's asking for it. No, it's obvious. It's really obvious. You just say it. Okay? I'm going to call it constant 1 because of the following reason. They say take V to be 0 at R equal to infinity. So when R is very, very large here, okay, V is equal to 0. So I cannot really take that constant to be 0. I cannot put it there, 0, because this is a voltmeter. This is actually a multimeter that measures, among other things, the volts. Okay, if I put this red into it in here, okay, this measures the volts in here. So the COM port in here, I can only put it in one place, this one. I cannot put it in two places. the black one in here. So I can only put it in one place. I'm holding the red one. Okay. So if I put it at infinity, that is where the voltage is 0. So if this C1 turned out to be 0, it's because of other constraints in the geometry. That's all. Like, for example, an equipotential or something. Other than that, it cannot really put C1 equal to 0. Does everybody understand? Now I have no choice just because of that thing that they gave me.
Yes.
Because they tell me to take V equal to 0 when R goes to infinity. That's what they're telling me. So V is 0, is constant. Now, I don't know much about it, but it has to be constant in such a way that it's continuous. The voltage has to be a continuous function in here in the boundary. So whatever V of RA is, at that point exactly is what that constant is. So this is the condition of continuity. But I don't know what V of RA is. So I need to find the potential in here somewhere between RA and RB. And we're asked to find that anyway. So let's find it between the two regions. V when R is greater than RA but less than RB. Okay. In that case, we have actually a Gauss's law gives me a charge Q, and we can use Gauss's law, and the entire sphere behaves like a point charge situated in its center, so that the potential in this case, or the electric field, is Q over 4 pi epsilon naught divided by R squared. But the potential then for the point charge is Q over 4 pi epsilon naught times 1 over R. But that's plus a constant too. Okay. So this is the potential outside the inner sphere, but inside the big hollow sphere, RB, okay? As long as I am there, this is the potential, but I have to add a constant. Remember, the potential is defined within a constant. But I cannot put that constant C2 also equal to 0 because I don't know at this point what the potential, what that constant is, because I know it at infinity is 0, but I don't know it there, how much it is. I can plug the value of RA in here and say that's a constant C1, but then it's going to be another relationship between these two constants that I don't know the answer to it. So ultimately, I need to work my way all the way out to find this constant business, okay? So we need to go to the outside completely. For R greater than RB, we know there is no electric field also outside because the charge enclosed is 0 too. So if I take a big Gaussian surface in here, E must be equal to 0 because Q is equal to 0. I mean, total Q is equal to 0. It's actually equal to plus Q minus Q. So it's 0, okay? So in this case, the electric field outside the 2 is 0. So since the electric field is 0, and if I take the antiderivative of 0, I find how much the potential now is. What is the antiderivative again? We're outside now. So 0 must be equal to minus dV over dr. So how much this constant now, how much this potential need to be for me so that if I take its derivative, I find 0?
Was it the constant?
It's another constant. Excellent. So it's a C3 actually. Okay. So I have a bunch of constants now. I need to find all of these constants. Otherwise, we didn't answer anything. We just left the thing ambiguous. However, now we know what C3 is because this expression is true no matter what R is, as long as it's greater than B. But if I take RB to, R to be very far away from it at infinity, this number better be 0. Okay, so this is 0 because when R goes to infinity, V sub infinity is actually 0. Okay, so since it's true anywhere outside to be a constant, then that constant better be 0. So the potential in here anywhere outside is 0. So V is 0 outside completely. Okay. In particular, it's 0 here too for this point RB. So because it's anywhere outside up to that point is 0, so it's 0 everywhere, including that point too. So we know that V of RB is actually equal to 0. But V of RB, I can calculate it a different way too. I can come back to this expression and equate it to 0 because that's from the inside, because that has no dimension. It's just basically a surface with no dimension, with no depth at all. So V of RB, I can say that this 0 also must be equal to Q over 4 pi epsilon naught times 1 over RB now, since we are at, this is true everywhere inside, including RB, okay? Plus C2 equal to 0. So from here, I can find what that C2 is. Do you guys see that I can find C2 from this expression? In terms of Q and epsilon naught and RB?
Yeah.
Yes? So C2 now is equal to minus Q over 4 pi epsilon naught times 1 over RB. So now we know what the potential is actually in the region is. In the region, let me write it with a blue sign in here. In this region is Q over 4 pi epsilon naught times 1 over R plus C2, and C2 is the same thing divided by RB now. What is R2 in here? RB, okay? So that is this number, RB. So the potential now in this region is equal to Q over 4 pi epsilon naught times 1 over R minus 1 over RB. This is true anywhere inside, okay? So we know the constant now. Furthermore, that value for the condition in here must be continuous. So it must be true also up to the point of RA. And up to the point of RA from the other side is equal to C1. And if I plug this value here for RA, then we're in business. So V from the inside, when R is equal to RA, must be C1. But when this expression in here, we know what it is. Q over 4 pi epsilon naught times 1 over R minus 1 over RB. But I have to put R equals to RA now for this to work. So C1 now, we know what it is. It's Q over 4 pi epsilon naught times a fixed number. This is a value. This is not anything else. This is actually a fixed number for C1. And that is actually the potential inside too, because the potential doesn't change inside. So this is for V true everywhere less than RA. It's the same constant, it doesn't change. So it's the same value in here and it stays the same. So the function then we're looking at in general is the following. V as a function of R is equal to, it's the same coefficient, by the way, Q over 4 pi epsilon naught, it's everywhere. For R less than RA first, it's this constant. It doesn't change at all. It's 1 over RA minus 1 over RB, okay? And this is a positive number, by the way, because RA is less than RB. So the inverse of RA, 1 over RA, and the inverse of RB, which is 1 over RB, is positive. The difference between them is positive. In between the region, it's 1 over R minus 1 over RB. Again, R is less than RB, so this is a positive number. So this is for R less than RA, and this is for R more than RA, but less than RB, and this is outside for R greater than RB. Makes sense, doesn't it?
Yes.
Correct?
Yeah, it really all comes together.
Yes, okay. So you have to work your way and come all the way till you find all of your constants. I worked my way from in and out because that's basically how they asked us the question, okay? Now take the potential to be 0. Show that the potential of the inner sphere with respect to the outer sphere is this. Okay, they want to find the difference in potential between the inner sphere and the outer sphere. So they call this one VAB. So basically find V at A, RA, and find the potential at RB and take the difference between them. That is the difference in potential. Well, exactly at RA, we could use this expression, or we could use this one, but plug in R equals to RA, it's the same thing. So that is equal to Q over 4 pi epsilon naught times 1 over RA minus 1 over RB. It's this whole thing. Now this one is 0, because we can clearly see it's 0 here, just at that point. So the difference in potential now between the inner and the outer is simply Q over 4 pi epsilon naught times the difference in these values. Period. End of story. That's exactly what we're supposed to show. So, because the outer shell is at 0 potential. So whatever the value of the inner shell, that is actually the difference in potential too. That's exactly what this statement is saying. Makes sense? Yes?
Yes.
Okay, question C, which I'm going to do, and then we're going to defer the question D to for some other stuff. It says that Use equation 23, and the result from part A to show that the electric field at any point between the spheres, and the gap between them is given by that expression. Okay. We know what the electric field between them is. I mean, the electric potential is between them. It's this expression. And the equation 23 basically says that because there is no theta dependence, there is no phi dependence. So basically the electric field now is going to be radial, and it's going to be minus dV over dr. Okay. So it's going to be minus d with respect to r of q over 4 pi epsilon naught. And this is between r greater than RA, but less than RB. Okay. So it's this value, this one. Okay. So if I take the derivative of that, which is 1 over RA, 1 over R minus 1 over RB. But again, this is a constant. 1 over RB is a constant, so its derivative is 0. The derivative of 1 over R is negative 1 over R squared, and negative 1 over R squared times a negative is going to be a positive 1 over R squared, and that's exactly what we're supposed to show. ER is going to be Q over 4 pi epsilon squared times 1 over R squared. However, they don't want to be expressed in terms of Q. They want it to be expressed in terms of VAB. They tell you exactly, show that it has a VAB in it. So for that, we're going to come back in here and note the following, that Q over 4 pi epsilon naught is VAB over this ratio of this radii, the inverse of this radii. So we're just going to plug that expression in here, and we are in business. So it's VAB over the inverse of RA minus 1 over RB times 1 over R squared. The advantage of writing it this way, of course, this is a radial electric field. The advantage of writing it this way is the following. By the way, the inverse in here is an inverse of a distance. So this is 1 over meter. Cancel the meter squared. So this is a volt over meter. So the units for the electric field are perfect in this case. But now using this device, I can find the voltage difference, V actually, 12 volt or 14 volt or 8 volt or 1.5 volt. I can find the value, and I can take a ruler and measure the radii of this, okay? Measure the distance, or the designer gives me the distance. So I can find the ratio here in meters, if you like, okay? And then I have an expression that doesn't matter how you calculate Q and all of that nonsense stuff. So you don't need to know Q. This is the advantage of this expression. This is a practical way of finding the electric field now, using a multimeter and a ruler. Makes it far closer, just like when you measure the speed of an object using a watch and a ruler. This is no different, except now instead of having a watch that is electronic, you have a device that measures the voltage that is also an electronic device. Powerful stuff, isn't it? Okay. Again, the task today, check and complete this problems. Okay, so that is what we're supposed to be doing in the discussion. As a matter of fact, the next item, they tell you that use the same expression to find the electric field outside. The electric field is going to be a 0 outside because of the fact that the derivative of 0 is 0. So I'm not going to do that part. So I assume that you guys have no problem with that. And also it tells you that use the what if the charge outside was not actually negative little q, but rather negative bq, which is not the same as big little q? You will notice that you can go back and do the analysis. The electric field, first of all, outside is not 0. The potential is not 0. Okay, because there is an imbalance in charges somehow. This is not a practical example, honestly. This is the practical example is for capacitors, and we will need this result down the road for a capacitor. But it's again, everything is going to be shifted as far as the potential. And you do it, and if you let me know if you have difficulty with it, okay? So this is problem 41. Problem 61 is identical, except the geometry is different. So this is 41. Problem 61 is slightly different. So let's do 61 quickly. The geometry is slightly different. So instead of having spherical, we have cylindrical symmetry now. So we're doing 61 now. Okay, so in problem 61, what we have coaxial cables. Basically, what your the cables you use for your TV are made up of, basically. And for telecommunications, we use that a lot. So you have a cable inside. It has a radius, not diameter, okay, A. And you have another cable outside. And this cable has a radius B. So let me draw them the way that they drew them, and that is a cross section. Basically, take a cable and you cut it now, okay? And you're looking at them from here. So this is the cross section. So in this case, this distance is A, and this distance is B, okay? I'm glad they dropped that RA and RB and all of that, okay? And they tell you that these are long cables, meaning you can use the result that we found way back for the electric field for that. So we know, where's the pen? If we go distance, I'm going to call it R. I know we used Y in the lecture, but we're going to call this distance R because they use the distance R in here, from the center of the inner cable, from this distance, basically. So this is what I mean by R, okay? And we want to find the electric field in that point. We found in class, if you guys remember, the electric field was lambda over 2 pi epsilon naught times the 1 over y, except we're not using 1 over y, we're using 1 over r. This is an electric field, not the potential. So Marcella, please pay attention to the power science, okay? And everybody else, okay? Because this can trick you. This can really trip you if you're not careful with this business of science.
Yeah.
Okay? Okay, so this is 1 over r. I'm glad you mentioned that because this is a lot of people basically get thrown off by this business of that. So, but if in doubt, go back to chapter 21 or 22 when we did this result.
I
Okay.
think because I've been practicing chapter 21 a lot, like I've been doing the practice problems throughout the chapters. So I've been so focused on the Q over 4 pi epsilon naught times divided by r squared. So I've been like doing a lot of problems like that. So then when you were doing the other one of the potential energy, I got thrown off. I was like, wait a second. But yeah, that makes sense.
Okay, thank you. Please, this minor detail can throw you off. This is the electric field. It has 1 over r for the wire, for an infinite long wire. And they tell you specifically that the axis of long wire, meaning use this result, okay? That's basically what you're supposed to say, okay? What they tell you also is that there is a lambda charge in here, and there is a negative lambda charge per unit length in here. So this will act like a capacitor because I have a negative lambda in here and I have a positive lambda in here, okay? So one of them is, so this is like a capacitor. The electric field actually will point this way, radially outward, from the inner cable to the outer cable, okay? And the potential actually will follow through too. So this is like a capacitor, and it is, okay? Except this is not a spherical capacitor, it's a cylindrical capacitor, basically. Not the plate capacitors that we did in lectures last time, but this is actually another kind of capacitors, and we will need the result in here, okay? So the positive per unit length, find A, calculate V sub R for R less than A, for R greater than A. Both of them are metals, by the way, which means that they are conductors, okay? So that means the charges cannot be on their inside. They must be on the outside. So even if this was a solid wire, there is no charge inside. So the electric field inside is 0. And because the electric field inside for R less than A is 0, how much is V then inside? What is the function if I take its derivative, I find 0? You can say it. I know you know.
Would it be a constant again?
Thank you very much. Have a nice day. Yes, absolutely. So we're going to call it C1, okay? Because there are no charges. It's a conductor. There is no electric field inside the conductor. Because there is no electric field inside a conductor, the potential must be constant. And they tell you also, I don't know if they hint, okay, what is the, They don't tell us about the electric field where to take it to be 0. We're going to take it to be 0. It's far away from the charges also. Probably I didn't read the whole thing, okay? There is an equal negative charge on the outer one. Calculate the net potential is the Shamsho, the potential. Okay, we're going to take V equal to 0 at infinity. So here, V is equal to 0 when R goes to infinity. That is typical of what you do in this kind of problems, okay? And so we're going to call it C1. So we don't know what that constant is. So it's going to better be called C1. Because if we take the potential in here to be 0, this is going to be a negative number. So everything will be shifted, okay? And this is going to be a negative number too outside. So we're going to take it 0 so that we have nice positive rounded numbers in here going from in and out. So that we see clearly we're going from a big number to a 0 instead of going from a big negative number to a smaller negative number or 0, okay? So in other words, this thing, you can put it anywhere you like, honestly, okay? And the difference will be the same. But at some point, this one would be a big negative number if this one was already a 0 or something, because you're going in the wrong direction, that's all, okay? So that's basically what this is. So I'm going to put it 0 out there because I know the positive is further away, so that it's going to go nicely from positive to 0, okay? Make sense?
Yes.
Okay, so it's a V, but it's constant now. I cannot put it 0 there because I put it 0 somewhere else. So now again, we're going to do the same thing in between them for R greater than A, but less than B. I guess you guys are seeing the similarity between these two problems. But except now the electric field has this expression, so the potential is actually going to be a little different in here. So the potential E, I mean the electric field A, which is minus dV over dr that is, that means V is the entire derivative of E dr, okay? Which means that V is equal to minus the integral of lambda over 2 pi epsilon naught, the entire derivative or the integral of 1 over r. What is the integral over 1 over x? Now you should know it from your calc classes. So V sub r is equal to minus lambda over 2 pi epsilon naught times, what is the integral over 1 over r? Or integral over 1 over x? You can quickly Google it if you remember, if you forgot it.
I remember how to do integrals correctly. It should be 0? No, because
The integral of 1 over x dx?
Oh, right. Yeah. ln. Yeah.
The ln of r plus another constant. Make sense? Do you guys remember this now?
Yes.
Okay. Yeah. So you have to remember those things because they come in handy. So it's the natural log. Okay. So the natural log plus C2, and that is V sub r. But I don't know, again, look, this business of a negative in here, so it's kind of annoying, but don't worry about that negative. It's going to be fixed quickly, okay? So this is for B between A and R. I don't know what C1 is, and I don't know what C2 is, but I know that they're constants. That's because I'm looking for the entire derivative. We're going to find them because we know where we put the port, basically. So we put it at infinity, far away from the wire. For R greater than B, then again, there is no electric field in there because no matter which surface I take, the charge enclosed in here is going to be positive lambda times this length. And this is the same thing, negative lambda times the same length. So the charge enclosed is 0. So the electric field also is 0 outside. If the electric field is 0 outside, that means that the potential is, which is minus dV over dr, must be equal to V is yes. What is the function if I take its derivative? I get 0.
A constant.
Another one. I know it's kind of sickening, but that's fine. Okay, I should say it. Okay, so it's another constant which we're going to call C3. As a matter of fact, C3 is true everywhere outside of these two cables. And then in this case, it must be true, since it's true at infinity to be 0, so it must be true everywhere to be 0. So as a matter of fact, this constant is 0 because V for r going to infinity is actually 0. Therefore, this constant, which is true everywhere outside r greater than b, then that means that C3 is equal to 0. End of the story. So we found C3 to be 0, and we come to the continuity of this expression just at that point B to make it equal to 0 too, because it's on one side for r less than b greater than a. At point RB, I'm sorry, V sub b, on one side it's 0, on the other side is actually equal to minus lambda over 2 pi epsilon naught ln of r, but now r is b, plus that constant C2. From here, we can find that C2 is actually equal to lambda over 2 pi epsilon naught times ln of b. This is C2. So now I have V sub r. All I have to do now is just basically rewrite V sub r for r between the two values now, not just at b. Is going to be V sub r is just equal to minus lambda over 2 pi epsilon naught times ln of r plus C2, and C2 is exactly this number, lambda over 2 pi epsilon naught ln of b. And now I have the common factor, lambda over 2 pi epsilon naught, which I'm going to take it out, lambda over 2 epsilon naught, and I'm left with ln of b minus ln of r. There is a property of the natural log, and log in general, is that the ln plus another ln is the product of the two numbers. In this case, it's actually minus, so it's the ratio of the two numbers. So V sub r then can be written as lambda over 2 pi epsilon naught, the ratio of the two lengths, b over r, okay? That makes more sense for the natural log because you don't want any arguments in the natural log. It's a function that takes no dimensions inside its arguments. Since I have the ratio of a distance b, the radius, over the distance r from the inner cable, then in this case, it's just a dimensional number. It doesn't matter which units you use, so they cancel out. The units for the potential in this case are lambda, which is Coulomb per meter, makes sense, divided by 2 pi epsilon naught. So this is the potential between the 2 points. We still need to find the potential inside because we said it's a constant C1. I need to find what that constant C1. And that on one side, for r less than a, for one side, V sub r, in this case, less than a, it's equal to C1. On the other side, just at the boundary, when r is equal to a, V sub ra is equal to, again, lambda over 2 pi epsilon naught times the ratio of a over b. I'm sorry, b over a. And this is a positive number. That's what I was talking about, where to choose the points in there. They matter because the ratio of b over a is more than 1, and the log of a number that is more than 1 is positive. So C1, which is the potential at the point A, is going to be lambda over 2 pi epsilon naught, the ratio of b over a. This is a number that is more than 1, and the function natural log is positive when the ratio is more than 1, negative when actually the ratio is less than 1, and when its argument is less than 1. And that makes sense for my choice of the potential in there being 0 at infinity, which is most of the time what we do anyway. So that is how we came up with this positive number. So that's why the potential in there is positive, okay? So we found the potential. Now we can write actually what the potential is everywhere. So V as a function of R is, again, the same coefficient lambda over 2 pi epsilon naught, which I'm going to put it out. Inside, it's the ratio of b over a for r less than a, or ln of r over, I'm sorry, b over r for r more than a but less than b, and it's 0 for r greater than b, okay? So this is the problem in here. They also, so it's just a summary of the previous steps in there. They also, to show that the potential of the inner cylinder with respect to the outer cylinder is given by that. Again, it's the same issue. The potential for the outer cylinder is 0. The potential for the inner cylinder is no problem. Okay, please watch the recording. I'm having problems with the recording, so please watch the recordings if you have to do something else quickly in there, okay? Anyway, so basically now we need to find the potential difference between the 2 points in here. V between A and B basically is equal to V sub A minus V sub B. And V sub A is this much times lambda over 2 epsilon naught, by the way. Lambda over 2 pi epsilon naught times ln of B over A minus V sub B, which is 0. So again, this is the potential, exactly how we're supposed to find it. That is VAB. Okay, correct? Yes? This is similar to the first problem. And then use the result from 2323, that equation, to show that the potential, basically, the potential, I mean, the electric field, we found it, and you can take the derivative of the ln, which gives you 1 over r again, and the derivative of this constant is 0, so you're going to be left with the derivative. What is the expression? The derivative of b, ln of b is 0. The derivative of negative 1 over r, negative ln over 1 over r is going to be what? Negative 1 over r. And there is a negative already in the definition of the potential, so that's going to fix the signs. So E is going to be minus D with respect to R of, again, lambda over 2 pi epsilon naught. They say specifically when R is bigger than A but less than B, of ln of B over A R. Again, the ln in here is just the ratio of these two numbers, which one of them is constant, the other one is negative. So this derivative in here is going to take, with respect to R, of lambda over 2 pi epsilon naught of ln of B minus ln of R. And this is constant, so it's going to give me 0. This is going to give me negative 1 over R, and then negative 1 over R times positive 1 over R, times negative 1 over R is going to be positive 1 over R. So basically, the electric field is going to be equal to lambda over 2 pi epsilon naught times 1 over R. Okay, but they don't want you to express in terms of lambda over 2 pi epsilon naught. They want you to express in terms of V over AB, VAB. So you have VAB over this ratio of the ln of this ratio. That is lambda over 2 pi epsilon naught, and that's going to give me now the electric field as they want it. So the electric field is going to be VAB over the same thing in here, ln of B over A times 1 over R. Again, this is identical to the first problem, except now we're doing it for the case of this geometry, and it's still the potential between the inner and the outer, the difference in potential, divided by some ratio, some properties of the geometrical properties of this capacitor. Okay, so this is basically in a nutshell what this whole thing is. So I hope you guys go through this problem, because we still have less than 15 minutes actually to finish the other problem. For that, I'm going to get Excel going. So that's problem 77, by the way. And let's go through problem 77 and see what we have in here. For problem 77, it says the electric potential in a region that is within 2 meters. I don't think we need Excel. We can do it by hand, okay? So they gave you the potential in here, but we need a calculator big time, okay? So they give you the potential in here as equal to ax to the power L plus by to the power m plus cz to the power n plus d, where a, b, c, d, l, m, and n are constants, okay? You need to find them, basically. And that's what they do. They tell you also specifically of some points in space, x, y, and z, and they tell you the potential in there and the electric field in there. So the potential for V0, 0, 0 is equal to 10 volts. So if I plug in 0, 0, 0, 0, 0, I find exactly D equals. So I will have 0 plus 0 plus 0 plus D equals to 10 volts. That means we found already D to be 10 volts. So we know one of these constants. This one is a check, okay? They tell you also that the electric field is 0 everywhere in this case. So if you take the derivative of this guy with respect to x, you're going to drop a power of L in here and you're going to find x to the power L minus 1. So we know x is L is more than 1. Otherwise, this is not going to be 0. It's going to be infinity, okay? They tell you also the same thing is true for the other two numbers. So they tell you basically that the electric field E in this point 0, 0, 0 is 0 as a vector. So for that to be true, really, L must be more than 1. M must be more than 1. And N must be more than 1. Because if they are not, then when you take the derivative, you're going to get a constant. So the answer is going to be constant, not 0. If it's L equal to 0. Or if L is equal to -2, for example, when you take its derivative, it's going to be 1 over x cubed. And when you put 0 for the x there, it's going to blow up. So that fixes the L and M and N that they are positive. So don't worry about the next step, okay? So that is part of the solution now. Now the next point. They tell you in the point of coordinates 1, 0, 0, the potential there is equal to 4 volt. 4 volt must be then equal to A times x to the power L. And x now is 1 meter to the power L plus 0 plus 0 plus 10 volt, because that's D. D is 10 volt. We found it already. So this is equal to 10. That means A from this equation is 4 minus 10, which is -6 volt, is equal to A times 1 meter to the power L. So we don't know what L is, so we can't really say it's -6 volt. So we don't even know what the L is, but we know it's more than 1. So A is equal to -6 volt per meter to the power L. So we need to find that L in order to answer this question. So this is not complete, by the way. So for that, we need to go to the electric field. They tell us the electric field E in that point 1, 0, 0 is equal to, if you look at the table in there, it's 12 volt, 0, 0. The other 2 points are giving me information that I already know, because we know that 0, 0 give me M and N greater than 1. But this 12 volt now is useful. Let's find the derivative of the electric field now from this expression. If I take the derivative of this expression with respect to x, I'm going to drop a power that is more than 1 multiplied by A, and now the power will go down by factor in here. So what I know in here is that minus L times A times x to the power L minus 1. This is EX, by the way, which is simply equal to minus the partial of V with respect to x. So this minus in here is coming from the definition of the potential. There was no minus in here. So this is the minus coming from this one. So that's where the minus is coming from. So this must be equal to 12 volt per meter. That is what the experiment is giving me. That's what that table is. But I know what A is. A is -6 volt per meter to the power L at that point. So this is for x equals to 1 meter, by the way, at this point. So now negative L times A, which is -6 times volt per meter to the power L, times x to the power L minus 1, which is meter to the power L minus 1, okay, is equal to 12 volt per meter. The negative and the negative cancel, and the meter to the power L and the meter to the power L cancel. And now I have volt over meter cancels the volt over meter. So this one and that one cancel the other one. And namely, I have 6L equals to 12. From here, I can find that L is equal to 2. So now I know what L is. I can come back in here and fix what A is. So this is the answer to L. I can come back into this expression and fix what A is. A now is equal to -6 volt per meter to the power 2, because L is equal to 2. So now we know exactly what A is, and we know what L is. So this point fixes this one and that one for us. We know this one already. So we need to still find B and M, C and N, and in the same fashion, basically, because I know we're basically exactly at the time. So let me do another point, and hopefully you guys can do the next one. So the next point in here, they tell us that for the next point 3, that E basically for the point 0, 1, 0 is equal to, again, same thing. Oh, we need to find first, so it's fine, 0, 12 volt per meter, and 0. But also they give us the voltage there too. The voltage at this point 0, 1, 0 is equal to 6 volts. So I need to come to this expression first to find the condition for my term B now, this term. So if I plug in 0 here, it's going to be 0. And I don't have to worry about now to the power L because I know L is more than 1. Actually, I know L is 2 actually in this case completely. And I know that N is more than 1. So if I plug 0, it's going to be 0. Plus D, which is 10. Plus B times Y, which is 1 in this case. This point has a coordinate 1 meter. To the power M. Where is it? To the power M must be equal to 6 volts. So on one side, it's 6 volt. On the other side, it's 0 plus B times 1 meter to the power M plus 0 plus 10 volt. 6 minus 10 is negative 4 volt is equal to B times 1 meter to the power M. So that means B is equal to negative 4 volt per meter to the power M. Please don't get confused, these two M's. There is this M, which is the power, and this is the meter. That's how this problem was set up, okay? Hopefully it's not confusing for you guys. But I don't know the answer because I don't know what M is. So I know the value is negative 4, but the units are kind of ambiguous at this point because I don't know what M is. For that, I need to go to the potential in here, the electric field, I'm sorry. So the electric field in the y direction, by the way, is going to be, again, minus dV with respect to y. And for that, the only term that is going to be picked up is the one with the term B, because that's the one that has a y in it. So I'm going to drop a power of M because I know it's more than 1. So it's going to be negative M, and the negative is coming from this definition, by the way, M times B times y to the power M minus 1. We know that this M has nothing to do with the meter, it's just the power, it's just a number. So it's going to be, the answer in here, they tell you that that field is 12, actually, if you look at it. So we know that 12 volt per meter is equal to minus M times B. And B, we found it to be negative 4 volt per meter to the power M. Negative 4 volt per meter to the power M. Times 1, because y is actually 1 in this point. 1 meter to the power M minus 1. Again, the meter to the power M and the meter to the power M, they cancel. And volt over meter, and I have in here 1 over meter in here, they cancel with this volt over meter. And I'm left with the unit M in here, which is an integer. Negative times negative is positive. 4M is equal to 12. That means that M is exactly 3. So we found what M is. 12 over 4 is 3. And now I come back in here to fix B and say B is actually negative 4 volt per cubic meter. So we have found actually what B is, and we have found what M is. So this is how so far the picture looks like for this potential. V is equal to A, which is negative 6 volt per meter squared. Volt per meter squared. Or where is it? Negative 6 volt per meter squared times x cubed minus or plus negative 4 volt per cubic meter, negative 4 volt per cubic meter times y cubed, plus we still have to deal with that C and Z, C and N, I'm sorry, CZ to the power N plus 10 volts. So in the same fashion, hopefully you guys can finish it. If you have difficulty with it, please let me know, because we have the same points in here. We have the point 0, 0, 1. We plug into it and equate the voltage in here. So this is 0, this is 0, this is 1 to the power N times C must be equal to, the voltage on the other side is 8 plus 10, of course, must be equal to 8 minus 10, which is negative 2. So that gives me an equation for C, which is going to be negative 2 volts per meter to the power N. Then I come to the potential, to the electric field, and take the derivative with respect to Z. This is 0, this is 0. The derivative of this one would drop an N times C times Z to the power N minus 1, and put Z equal to 1 meter again, and cancel the units, and I will have negative 2 on the other side. time is a negative, which is coming from the definition of the potential. So it's going to be a positive 2 equals to basically 12 in this case. And that is going to give me the power of 6, actually. So the answer in here is going to be C, which is going to be negative 2 times z to the power 6. So to verify that the expression at the end for the electric field, I mean the electric potential, is going to be equal to negative 2 volt per meter squared, x squared, I'm sorry, plus negative 4 volt per meter cubed, y cubed, plus negative 2 volt per meter to the power 6 times z to the power 6 plus 10 volt. And again, you're supposed to take the derivatives of this stuff and finish it and all of that, okay? Okay, so hopefully this is plenty. I know we took about 5 minutes, 7 minutes from your time. Okay, so hopefully you guys can finish these problems, and please let me know if you have difficulty with them, because we're going to move to the next chapter next time around when we meet chapter 24. Okay, on the capacitors.
Alrighty.
Okay.
Thank you again, Professor, for today. We're having lab, right?
Yes, we do.
All right.
No, I'm sorry. We're, no. We can't. We don't have anything ready for it yet. Okay?
Oh, okay.
I'm going to send a message. Thank you for reminding me.
Alrighty.
Okay, thank you.
Thank you.